Okay, today we're going to be talking about electric dipole. What is an electric dipole? An electric dipole is simply two charges of equal and opposite signs. This is a negative charge, this is a positive charge separated by a distance. So this is what we call a dipole. A negative charge, a positive charge, two equal and opposite charges separated by a distance. So if this is 3 coulombs, this will be minus 3 coulombs. If this is 4 coulombs, this will be minus 4 coulombs. So now, what should we know about this electric dipole? The first thing we need to know about electric dipole is the dipole moment. The dipole moment is simply written as P. It is equal to 2 multiplied by the distance, or let's just go this way. Let's go this way. The dipole moment P is equal to the distance. Let's just assume this is the distance between the two charges. So the distance between the two charges multiplied by one of the charge. But in so many books, they like dividing this distance into two smaller distance, A and A. And if we join this A, we have 2A, and 2A is equal to D. So we could still write it this way, 2AQ. So these two formulas means the same thing. So this is what we call the dipole moment. Now, if a dipole is placed in an electric field, let's just say this is the positive side of the dipole, this is the distance between it, and this is the negative side of the dipole. The dipole will feel this tendency to rotate. Why? Why will it feel this tendency to rotate? This is the positive side of the field. This is the negative direction of the field. So this negative component of the dipole seems to shift to this positive, and this positive dipole feels a force that shifts to this negative. And at the end of the day, you see, if this is the dipole feels this tendency to turn, to bend this way, and that is actually called, it feels something like torque. Torque is actually force times radius. So it feels force times radius, the torque, the tendency to just rotate. So another concept comes into this topic, which is torque. Torque is simply, I'm not really going to prove it here, or you can just check the app. It's written this way, is equal to P multiplied by electric field. It's just a very simple proving. Because of time, you can check through the app. I just gave the step-by-step method of getting torque. So what does P stands for? Remember I told you dipole moment. So dipole moment multiplied by the electric field intensity E. So but when this dipole is at an angle theta, the Americans are going to call it theta. So theta, when it's at an angle theta, you don't get maximum torque. So the formula is written this way: torque is equal to P E sine theta. So whenever they ask you an equation relating torque, if it involves an angle, you use this formula. If it doesn't, you use this. So let's just touch one question. Now let's look at this question. based on torque. They say the HCl, hydrogen chloride molecule, has a dipole moment of about 3.4 times 10 raised to the power minus 30. That's what the Americans will call it, or 30 cm. This cm is not centimeter, it's actually coulombs meter. That is the unit of dipole moment, coulombs meter. So the two atoms are separated by about 1.0 times 10 raised to the power minus 10 meters. What maximum torque would this dipole experience in a 2.5 times 10 raised to the power 4 Newton per coulomb electric field? So we need to take note of these points. They gave us dipole moment. They gave us a distance between the two atoms. And they're asking for the maximum torque. So the maximum torque is simply equal to, okay, I think my brain is kind of glitchy. The maximum torque is equal to dipole moment multiplied by electric field. So if the torque is not maximum, then we put sine theta. That's when the torque is bent at a point. But for us to get a maximum torque, we just need to multiply dipole moment multiplied by electric field. So say the dipole moment is 3.4 times 10 raised to the power of minus 30. Then we'll multiply this by the electric field. Electric field is 2.5 times 10 raised to the power 4. So if we punch this correctly in our calculator, I think we need to be getting 8.5 times 10 raised to the power of minus 26 Newton meter. Remember, from last semester's physics, Newton meter is the unit for torque. So that's that for now.